gravitational field inside a uniform spherical body. Let us try to work out the gravitational field inside a uniform spherical body. So let's have a picture here. Here we have a uniform spherical body, and let us assume that this is the center of the body, and let us consider a point at a distance r from the body. We call it P. So we will just draw another circle inside to indicate a segment of the sphere. Doesn't look nice. Try again. It's a little bit difficult. Okay, let us assume that this is perfectly matching the center. So let's assume that both are perfectly spherical. It's a little bit difficult. Let's consider a point here. This is the point P. We need to work out the gravitational field strength at P. So assume that the radius of the original sphere, let us take it as capital letter R right here. And the inner sphere, definitely, that is inside the point P, let's take it as small r. And now, small r, this is capital R. Now, the idea is that for a uniform spherical body, gravitational field strength due to the outer segment would be zero. I will mark that point, I will mark straight that region. So look at this shaded region. The gravitational field strength due to this outer segment would be zero because every point the gravitational field will cancel out with every other point. The gravitational field strength is a vector quantity. You can think about it and see whether you understand that idea. So this outside region would not contribute to any gravitational field strength at P. So only the inner sphere we need to consider. Let us assume that the sphere is having a mass m, and in a sphere the radius is small m. So this small m will contribute to gravitational field strength at P. So this is the idea. The segment, of course, it is shaded outside P, that's the name of the point, does not contribute to the gravitational field strength at P. So we need to consider only the inner mass. The rest is pretty simple. So we can assume that the gravitational field strength at P is equal to, let's put it as G dash, comes only due to the mass of the inner sphere, that is equal to, we don't consider the vector aspect, we will consider only the magnitude. So we can write it as a positive quantity. So we can write it as G times small m times r square. Now we need to find out the small m. We know the total mass of the body is capital M. So you can write small m is equal to, because it is uniform sphere, capital M over 4 over 3 pi capital R cube times 4 over 3 pi small r cube. We simplify this and you will get small m is equal to m times r cube over capital R cube. So let's put it as equation 1 just for the convenience, so we can do the rest easily. So we can work out G dash value now. G dash is equal to, we already know that Gm small m upon r square, so that is G time or G over r square, it's a small letter r square, times m value is given by m r cube over capital R cube. So r square and r cube cancel out. You get the expression. You get g dash is equal to, what would be that? G will be there. G m over, let's say, r cube times r. So what you can see here is that g is proportional to this. G dash is directly proportional to r. It's a linear function. Let's try to plot the magnitude of the gravitational field both inside and outside. This is how it looks. This is the graphical description. Let's put a graph in here. All right, here we have the y-axis, which gives you the gravitational field strength, and here we have the x-axis, that is the distance from the center of the sphere all the way to infinity. So I'll just push it a little bit up. So here I can write, this is the g value including gravitational field strength both inside and outside. We will plot it here. Here we have the r value, that is in meter. We can mark the radius of the sphere, capital R, somewhere here just for the convenience. Let's put it here. Let's mark it as capital R. Let's draw a dotted line down here. That's pretty tricky, but I will try anyway. Okay, here we have that. This is the boundary. This describes the R value, indicate the R value, the boundary of the body. R value. Okay, it is something first. All right. Now, inside the gravitational field is linear, so it's a straight line. So you can draw a straight line in here. This is only the magnitude of the gravitational field strength. The expression here would be, I'll write again g dash just for the convenience. It's g in here, but it is what we have already had, g m capital M equals capital R cube, and then it is multiplied by R. And outside the sphere, it will be exponential, so I can draw it exponential. So it's a little bit tricky. I will try. Here we go. So this is outside the sphere. We can write G is equal to G M over, doesn't look nice, G M over R square. So that's an exponential graph. So this is the description of the gravitational field strength both inside and outside a perfectly uniform sphere. Now let's go to another topic, that is about escape speed. Let's talk about escape speed. What does it mean by escape speed? Usually represented by v or v. I would mark it as v just to differentiate it from other speeds. V escape. Now, what does it mean by escape speed? This is the minimum speed. What is this? Minimum speed with which a body need to be shot up from a planet, not necessarily a planet, any celestial body is fine, so that it escapes the gravitational field of the planet to go to infinity. To infinity. This is the idea. You can make it short. You can just write this is the minimum speed with the body should be short at so that it escapes the gravitational field. This is pretty simple if you know the idea of gravitational potential energy. Now look at here, let's consider this is the planet and we are going to shoot up a body so that it reaches all the way to infinity. So how much energy we need to spend or how much it should be the minimum speed required. Let's assume that here we have a small body of mass m, small m, yeah, over the surface. Now we are going to send it all the way to infinity. Here, not necessarily along a straight line. You can use any path. It doesn't really matter because energy does not depend upon the path taken. This is conservative field. Gravitational field is a conservative field. Infinity all the way. Doesn't look nice. All right. So this goes all the way to infinity. So suppose we assume that the mass of this, for example, this is Earth. Let's assume that this is Earth. Need not be Earth, any other celestial body. This is fine. So assume that the mass of the Earth is m and the radius of the Earth, let's take it as r. We know the values approximately, or at least we can find it out. I don't remember the values though. This is the radius of the Earth. Now here the potential energy of the body of mass m. So I'll write it as potential energy of m on the surface of Earth. In this case, we assume that it is Earth, not necessarily Earth. Surface of Earth, that is equals to, we already know the value, minus g, it's negative, minus g m over r. Now, the potential energy of the body at infinity, the potential energy of m at infinity, that we already know the value, that should be 0. So change in potential energy, change in potential energy, that is equal to minus gmm over r and 0. So 0 minus gmm over r. So you will get this equal to g m over r. So this is the energy we need to provide the body with so that it will reach infinity. So we can just write the initial kinetic energy half m v escape square. This must be exactly equal to the increase in the potential energy, that is equal to g m over r. If we simplify this, we will get the escape speed. I'll write it here, escape speed. We can escape speed VE is equal to under root 2 goes to the top, m cancel out, you will get the expression 2 gm over r. This is the expression for the escape speed. For example, in case of Earth, we may substitute the values. Mass of Earth is equals to, if I remember, approximately 6.0 times 10 to the power 24 kilogram. Radius of the Earth approximately is 6.4 times 10 to the power 6 meter. You can cross check it. And of course, G value is equal to, I think it is 6.64 or 67. I don't remember. Check it again. Times 10 to the power minus 11. Substitute the values and you might work out the escape speed, and I think it should come around. I'm not sure, you need to check it. 11.2 kilometer per second. Now this is not actually worked out by me. I just got these values from my memory. It may be wrong. So you just need to work out and see whether I got the right values. If I got a wrong value, you use your own values. So if you shoot a body with a speed of 11.2 kilometer per second from the surface of Earth, it will break the gravitational field and go all the way to infinity.